Thank you very much for the nice introduction and thanks for having me here. It's a great honor for me to speak in front of you, and I will try to speak slowly and clearly that hopefully everybody can follow. I was asked, so I'm from Germany. I was asked to talk a bit about the German industry. We heard many use cases of Apache IoTDB, and all of them, I think, were from China, where IoTDB is quite popular already. And I will share two concrete use cases that we have done in Germany. So, what do I want to talk about? First, I will talk shortly about digitalization in Germany. It's very impressive for me to see how companies in China handle things, and I will talk a bit about how things usually go in Germany in the industry. Then I will shortly present you a framework, the Open Machine Platform that we are developing to help integrate IoTDB in applications. And then I have two use cases, one about fuel cell application at the German Railway Corporation, and one called Smart Core, which is an application of foundry, automotive foundry. So, where are we at in Germany? This is the age distribution of the German workforce. And as you see, it's skewed a bit towards the right. So the average age of a German worker is 45 years, which on the other hand means that those people usually are not super IT affine and super IT experienced, which is kind of a burden for us to introduce new technologies. The second slide here is the age of the typical German machines in our plants. So the typical age of, the average age of the machinery in German plants. The average age is over 11 years. So our assets are quite old, which has the downside that the control systems in those machines are very old. So this is a typical example, Siemens S7300 device, which is very common in those machines, and it's very hard to interfere with these devices and to collect data from those machines. And the last aspect, for me it was really interesting to see how many use cases in the Chinese industry really focus on the data in depth, because a lot of companies in Germany don't have designated data scientists or people that are able to work with the raw data. So we usually have to aggregate the data quite a bit so that the operators on the machines or the leaders of the shifts or the managers of the plant get their information out. So this is nothing that typically German companies do by themselves. So these are typical examples of the results we have to provide, which is just some numbers about throughput, efficiency of the factory and things like this. And this leads me to the next point. So we do not focus so much on the raw data, and sometimes we don't have that much data. For us, it's more important to have a nice integration in the sense of full stack, so that we are able to provide our customers and these companies with exactly what I said, from the data collection up to calculated metrics and KPIs that they are interested in to run their plant more efficiently. And usually when you develop this kind of solutions, many of you might notice, then you need very basic things. You need user management, asset management, then of course data management for time series data we will collect. We need some kind of analytics system or calculation of metrics. And as I said, it's quite important for us to have a nice visualization, which is suited not only for experts, but for regular people that do not look at these kind of charts daily. And because we are now in the domain of probably classical application development, the developers dealing with IoTDB oftentimes are no database experts. They are regular developers, web developers, backend developers. And as Django is quite popular in this area, one of the first things we did was to develop a framework called Django IoTDB, which makes it very easy to integrate IoTDB with Django so that you don't need to be an expert in IoTDB and the query language. So we have an abstraction which makes it quite easy to fetch data without the need to fully understand the syntax with all its details, how does the group by work and things like this. So this makes it way easier, more accessible for developers to write applications that are based on IoTDB. Another thing that we have developed is a framework we call the Open Machine Platform, which solves exactly the problem I've talked about earlier, that we need a certain set of preconditions, user management, asset management, all these things. So this framework basically serves as the baseline to start off for the kind of project I've talked about. So here you see a bit of the architecture. What is very important for us is the thing called PLC server, which is based on another open source project, Apache PLC4X, which is right at this time presented in the other room, which we use to gather data from those different machines. And then on the left side, you see the structure. It's based on several modules. Very important for us are things like rule-based access control, the device management, also analytics. And then we have this part here, I don't know if you can see it very good, which says apps and extensions. So basically, when we start to develop a solution, or other users of this framework, as it's open source, start to develop a solution, you get all this basically for free, and then you start with really what you're interested in for your specific domain or your specific field of application. And now I move over to the first example, which is based on the architecture I've just shown, which is a project called BZNEA with the German railway company. So the Deutsche Bahn is roughly similar, I guess, to China Railway Corporation. So this is a government-owned entity which takes care of everything related to trains and infrastructure. So passenger transport, freight transport, and all kind of infrastructure management. So for the train stations, for the rails, everything. And they started 2 years ago a project, BZNEA, where they want to replace the backup power generators that are currently run by fossil fuels with fuel cells. So in many areas in the German train system, when there are big switches and the areas are very rural, then there are some backup power generators which in case of a problem with the energy system will power the switches and ensure that the train system is still working the way it's expected to do. And as we move towards carbon neutrality, the goal is to replace these backup generators with fuel cells. This is an example of how such a generator looks like. So this is just an example, very rural area. Here's the necessary hydrogen. And as some of you might know, fuel cells are quite a complex technology compared to regular combustion engines, which we do since more than 100 years. So we have to manage different kinds of media, and we have to take care of many operation parameters, which makes it very important in this case to have a good monitoring. This is another example, and this looks at least way more complex than a regular combustion engine-based backup generator. And before I go into the details of the solution, there's another thing in Germany. I mean, you might know that in Germany we have many regulations regarding data protection, GDPR, but there's also another kind of regulation which is important here, which is called kritis. So the kritis is a term which roughly translates to critical infrastructure. So with very special regulations for all software that is used in critical infrastructure. And the German train system is considered such an area. It's considered critical infrastructure. So we have special requirements regarding security that we have to meet. This is an example, or this is the diagram of how the system looks like. You might notice that it looks quite similar to what I've shown earlier. Besides, the PLC server was replaced by an MQTT broker, because in this case, all those stations sent the data by themselves directly from PLCs from all over Germany. So on the right side, we have a connector which ingests the data directly into Apache IoTDB. And the major difference that you can see here basically is that there's a connection between Apache IoTDB and the role-based access control module. And yeah. So of course the front end basically is pretty similar to many applications we have seen today. So we have ingest data and we digest data or display data in several different ways. But due to the special kind of regulations we have, we cannot only use user management in the front end, which then queries the back end, but we have to provide a user management down to the database level, basically. And in IoTDB is a module, I don't know how known or common this is. There's a framework which is called pluggable authorizations. So you can provide your own implementation for the authorization. So whenever an operation is performed in IoTDB, might it be a read or an insert operation, then this module is checked to see if the user that sent the request has the appropriate permissions for this device or this time series. It defaults to a file system-based solution, but there's another implementation we did, which is called OpenID Token Authorizer, which, this is an example of the implementation, which means that if a request comes from the front end, it has an OpenID token or a JSON Web Token, and then we pass this token also to the database. And then on the database level, we ensure, and then you see here, on the database level, we have some code which takes the token, identifies the user, and then checks the rights for this user to see if the request the user has requested is appropriate or not. And this is a nice possibility for us to really enforce these very strict regulations with very little effort that we need to do. Now I'm going over to the second use case I want to present, which is called Smart Core, which takes care or which takes place in a foundry. I think this use case might be interesting because it's from the automotive industry, from the German automotive industry, which is usually an industry that many people look at, what they do or how they do things. And this project is about one of the foundries where motor blocks are produced, 4 and 8 cylinder blocks. In each foundry, usually there's a part of the foundry which is called a core shop. This is the place where so-called sand cores are made. I'll go into detail a bit later. So the parts that are produced, those motor blocks, are very complex and have very complex inner structures for cooling liquids and cables that go through it and stuff like this. And those parts can only be produced efficiently with the help of sand cores, which are this is an example of such a sand core, which are placed inside inside the part during the molding process, and then after the molding process, the sand goes away, and then you have the holes in it. So this is a standard procedure for everybody who knows low pressure casting, and this is a very interesting process for us because it's a very complex process. In one single foundry or in one single foundry line, we have up to 10 of those machines, which are called core shooting machines, which basically produce those sand cores. And those machines have over 200 sensors. And the processes that happen in these kind of machines during the shooting process are physical and chemical processes, so there are chemical reactions, but also high physical influence, like temperature and pressure. And those processes happen in several time scales, from microseconds when the sand is shot in the toolbox, up to several seconds or even several hours when the sand is treated afterwards in a cooling process. What we do here in this process is a central aggregation of all those time series, and then we use those raw values, those raw sensor values, to do aggregations to provide metrics which help the people to run the factory more efficiently. So the architecture is, this is a picture you've seen before. The architecture is again based on the Open Machine platform. Here we have the PLC server, and we have an analytics framework which takes all the data we get from the PLCs and does the necessary calculations to provide the kind of metrics that the customers need. The most interesting part from an IoT, I mean, it's a pretty standard IoTDB application, I would say. Perhaps the most interesting part is happening in this area of the graph, where we use Apache Flink as a stream processing framework, which is, I think, a pretty common pattern. But with the recent developments in Apache IoTDB, we are trying to migrate towards an approach which is based on user-defined functions, continuous queries, and triggers, which would then push all analytics on the time series inside the database, and we could eliminate one part of our application. So this is a picture I've shown you before. Basically, this is the result of the analytics we do. So based on the information we get from the sensors, from the PLCs, we calculate metrics like productivity, quality-related metrics. We also generate several reports about the manufacturing process, which are used for quality inspection, quality control. And another aspect which is quite important in the automotive industry, automotive industry is pretty much all about production costs. Production costs is a crucial part in efficient manufacturing of cars. So they do pretty extensive calculations. And during this core shooting process, you have several media that you use. You use water, you use compressed air, you use energy, you use sand, and you use some chemicals, additives, that they are called. And up to now, they just did a global calculation of how much material they used over a week, how much parts they produced, and this is what they've done. Now we have the possibility to drill down those values basically on every single core shooting process. So one part or one type of core is more likely to fail, more likely to break because it's more brittle perhaps or more complex, then of course it will consume way more sand because some of those cores have to be thrown away. And this is a module which is quite important because we on a daily basis generate all those reports to say which order, which part, which sand core consumed how much energy, media, and so on, which is then used for pretty strict calculation about the costs of the manufacturing process. Another aspect we do here is from the parameters we read from the machine, we know things like which toolbox is equipped on the machine, we know the quality of those sand cores, we know the exact treatment of the sand cores. So we can use this system also to control processes that happen later. For example, we automatically generate orders for SAP, so for the ERP system, and also for the warehouse, without the need to have any other integration layer, just out of the data, because we know what kind of cores and which quality they are, so we can automatically tell the warehouse where to store them and where to provide them later on. This brings me to my summary. Sadly, I would say the adoption of the digitalization in Germany is still slow compared to what I see in other countries and what I've seen today or in the last days here in China, due to various reasons that I've talked about. Perhaps it's also a mentality thing, but it really is also related to the fact that our industry has a long tradition, which is a good thing, but on the other hand, this means that our assets are sometimes a bit older, which makes it harder to integrate them into these processes. And another thing is, as I've told you, that the German companies, even in the automotive area, are not yet at the point where they have their own teams which do the data analytics by themselves, but are more focused on the very classical plant management, which imposes the burden of us. If we want to introduce them to IoTDB, then we can not only provide them a database and say, hey, this is a good database, you can store your data in it, but we have to do the full stack in the sense that we have to come up with a complete solution from data collection up to evaluation of the metrics. And as I've also said, the applications are not too data heavy because we cannot collect all data from all machines, especially not from old machines. And on the other hand, the granularity of data we need for these kind of analytics is not that high. So we are certainly not pushing IoTDB to its limits with these kind of applications. And as I've also said, the integration is very, very important. So we also created those frameworks to help other companies build their own solution based on IoTDB without having the same boilerplate to be written over and over again. And another aspect which I really want to emphasize, because it's important for us, is that there is the possibility to extend IoTDB in a way which makes it feasible for basically every application. Here in this case for the critical infrastructure application in Germany. And another factor which helps us in this case is the nature that IoTDB is open source, of course. So basically this sums up my talk. Thank you.